My name is Ben Shao. I am a structural analyst in the Advanced Technology and Research team of Arup, San Francisco office. And today I'm happy to deliver this webinar for you and talk about the LS-DYNA applications in civil and structural sector. This is a pre-recorded webinar, but if you have a question, feel free to contact me later directly through my email shown on the right corner of this slide. So the main reason or the purpose we have this webinar is really to demonstrate the capability of LS-DYNA for civil and structural applications in the built environment and to demonstrate how LS-DYNA can be used in daily design and analysis work through real-world applications done by Arup. So for this webinar, I will first do a very brief introduction on LS-DYNA's capability in civil and structural applications. And for the rest of the time, I will talk through several projects where LS-DYNA simulation has been heavily used for design and analysis process. And these projects are real industrial projects conducted by Arup's offices around the world. So when we talk about civil and structural applications, there are many different disciplines, and LS-DYNA can be applied to a wide spectrum of application. And today I will focus on three areas or from three perspectives, including firstly, the building seismic analysis, which is one of the most common application in seismic analysis and design, especially when we consider the concept of performance-based earthquake engineering nowadays for many design projects. And the second area I like to talk about is the geotechnical application, which really shows the unique advantage of LS-DYNA when tackling complicated and large-scale geotechnical problem and soil structure interaction. And the third area is some special analysis applications in civil and structural sector, which does not focus on traditional large-scale building and geotechnical system analysis, but really shows the variety of different types of investigation LS-DYNA can be applied to. So throughout these discussions, I like to demonstrate the strong capability of LS-DYNA on numerical simulation for civil and structural applications, and to showcase that it has been extensively used already in real-world projects. Hopefully this can give a good idea to people who might work in this area but might not use LS-DYNA as their primary simulation tools and wondering how capable LS-DYNA is in this type of application. So as many of you probably know that LS-DYNA is a three-dimensional nonlinear finite element analysis program owned and developed by LSTC, now part of ANSYS group. And it is really capable of computational intensive time domain multiphysics simulation. Although initially conceived for just modeling, short duration events such as say impact and blast in the military and mechanical engineering areas, but the program has been really extensively developed to cover a wide range of applications, include analysis on civil engineering structures, like soil and soil structure interaction, loading by earthquake, or long duration events such as movements due to construction. So first, I like to briefly just talk about some general capability of LS-DYNA relevant to civil and structural applications. So firstly, LS-DYNA has very strong or robust explicit and implicit solvers, which are perfect for linear, nonlinear static analysis and linear and nonlinear dynamic analysis. For example, earthquake response history analysis, which we usually need for seismic design and assessment. And secondly, LS-DYNA has very strong capability for parallel processing. This is actually very important when we tackle complex 3D modeling with large number of elements and complicated model behavior. And this will really significantly reduce the computational time. And when modeling behavior of structure or soil materials in civil applications, capture the complex nonlinear behavior is very important. So LS-DYNA has strong capability for modeling nonlinearity in engineering materials like cyclic degradation, failure, and other complex behavior. For example, it can well capture the cracking of concrete, like fatigue of steel or poor fluid behavior in soil and liquefaction and so on. And LS-DYNA can achieve this through a large library of advanced material model and element formulations. It can also capture other complex modeling issues such as context, response under large deformation. And then it has a very large library of outputs, and the user can really extract any information they need for design and assessment, from material level local response to element and global level responses. So it gives a great freedom to visualize, extract, and post-process all types of simulation results which are meaningful to the users. So comparing to other simulation packages in civil and structural field, LS-DYNA has really significant advantages as discussed in many aspects. And in terms of Arup's involvement, so Arup has over 35 years of experience and expertise using LS-DYNA for a very wide spectrum of discipline, not only just the civil and structural applications we talk about today. And we have been working with LSTC, now ANSYS, since like mid-1980s. And we developed many capabilities of LS-DYNA for the civil structural engineering sector. For example, advanced material model for concrete and soil, and construction stage analysis to, say, remove soil and adding structures to simulate the construction process and so on. And we also distributed LS-DYNA in the UK, India, China, and US. And another development we have is we developed and also market our own pre and post processor for LS-DYNA. It is a suite of software called Oasys, which are used by many LS-DYNA users now. And recently, we are also focusing on developing new features, especially to support the civil and structural practitioners' daily work if they use LS-DYNA. For example, a model converter from design software such as ETABS to LS-DYNA, and post-processing module for structural response check. So hopefully this gives you a very good overview of LS-DYNA features and capabilities for civil and structural applications. And in the remaining of this webinar, I will talk through some example to really showcase these points I just talked about through real-world project applications. And the applications shown below only focuses on the projects done by Arup's office globally. So special thanks to my colleagues for providing the information for their projects for me to talk through. So the first application area, as I discussed, is for seismic building applications, where LS-DYNA simulation is often used to model the building structure and simulate its behavior under seismic loading in either new design or performance evaluation of existing building. So the first project I'd like to talk about is the Loma University Medical Center, as shown in this picture. This is a large building, very large building with 17 stories, as you can see in the picture, and sits adjacent to the active fault in California, US, which has very high seismicity. And as you can see on the left, the superstructural system is buckling resisting brace frame and moment frame for the two lateral directions, respectively. And so in order to achieve the desired performance under the extreme seismic condition, seismic isolation system is used, which consists the triple friction pendulum isolator and viscous fluid damper to control the horizontal displacement, as shown on the right. And in order to demonstrate the seismic performance, as well as do the detailed check of component behavior against acceptable criteria, LS-DYNA nonlinear response history analysis was extensively used in this project. So the 3D LS-DYNA model has been established, and all main lateral frames are modeled nonlinearly. you can see in this picture, this is a picture, a snapshot for the 3D model. And for the superstructure, the frame beams and columns are modeled with resultant nonlinear element, similar as what we typically use in, say, Perform 3D. You have that hinge element, but LS-DYNA with that resultant beam element, it has more advanced capability. And the BRB braces are also modeled explicitly. Effects such as kinematic hardening can be captured, and the connections are modeled with constraint and special treatment to mimic the rigidity, and slabs are modeled with shell element to provide expected rigidity both in plane and out of plane. So one of the important part of the model is the isolation system. And for horizontal isolator, we use the advanced isolator type material in LS-DYNA, which has the most advanced feature for modeling triple friction pendulum isolator, including the failure of rim even, and their large horizontal displacement. And the dampers are simulated with damper element with displacement lockup modeled. So to validate the modern procedure of the isolation assembling, we also did a validation study against the shaken table test. So for this project, a large number of response history analyses are conducted to demonstrate the responses with different model configurations. So this is a perfect example showcase LS-DYNA's usage in performance-based earthquake design application and modeling sophisticated 3D behavior of buildings with significant nonlinearity happens. And the next example I like to talk about is the Raffles city, ChongQing, which is the iconic structure in Chongqing, a big city in China. As shown in this picture, the structure has a unique configuration where 4 towers were joined by a vessel-shaped conservatory at the top. The unique design challenge is the linkage between this conservatory and the 4 curved and slender towers. So when we think about this linkage, different options are available. For example, for this CCTV tower shown here, which is also one of Arup's past projects, it is monolithically linked. And for Marina Bay Sand, movement joints between the towers have been introduced so that they are seismically independent. And for this project, it was decided to have seismic isolators at this interface, which allows the relative movement between the conservatory and the 4 tower. And a dynamic linkage was considered with a combination use of friction pendulum isolator and damper as shown on the right. And an important step in the design process is really to validate this proposed linkage idea and conceptual design, and to validate the structural responses under different levels of seismic loadings. Meanwhile, the design scheme of the isolator and damper needs to be optimized, and these are all achieved by using detailed LS-DYNA model in the design process. As shown in this animation, the complete LS-DYNA model was developed and consisted of about like 825,000 elements. And everything is modeled explicitly, you can see in this animation. And all lateral members were modeled nonlinearly with advanced material models. So the LS-DYNA analysis provided important information to the design team, especially to understand the expected level of responses and at component level. For example, this picture shows the sample results from the component level responses for all columns and beams, and the plastic rotation responses are checked and plotted against the FEMA criteria, which define different levels of structural performance based on plastic rotation thresholds. Over the course of this project, there are more than 1,000 analyses were conducted to support the design, which really shows that LS-DYNA is heavily used by the engineer to facilitate the design process. So I have talked about 2 projects so far which use LS-DYNA as an important tool in the design process for the iconic large-scale structures and to solve the challenging design issue and help make design decisions by providing advanced simulation capabilities. And on the other hand, there are lots of situations we need to understand the performance of the existing buildings to make retrofit decisions based on the performance and to protect life and reduce possible financial loss in the future seismic event. So the first example I like to show is a project we did to assess the collapse probability of a large number of non-ductile concrete buildings. You can see from the map there are many buildings considered, and in order to capture the collapse behavior, to understand the behavior, it is very challenging as there are many failure mechanisms expected for an old concrete buildings as shown on the right. So thanks for the advanced modeling capability of LS-DYNA, we construct the 3D LS-DYNA model for each of the building based on the drawings, as you can see in the map now, and capture all these failure mechanisms in the simulation to assess how the building can fail and collapse during seismic shaking. So for example, we model the concrete shear wall, as you can see here, using multi-layer nonlinear shell elements, a very advanced kind of modeling procedure for shear wall to capture the rebar and concrete in different layers. And this modeling procedure not only capture the global behavior of the shear wall, but also the local stress strain level responses. And we model the spandrel beam. This is quite common in this type of building with also shell elements to correctly capture the possible shear and bending failure. And the beam column joints, as you can see here, is also explicitly modeled using special constraints. And this shows some animations of several buildings in LS-DYNA, and you can see that the progressive failure was captured, and it really provides significant value to the client because it is not only just simulate the building collapse, but also tells where the deficiency of the building is through the simulation results and provides significant value and guidance for the retrofit design. And these models actually are directly used later again to support the retrofit work conducted by the local engineers. And another example regarding assessing the performance of the existing building is a large-scale project we conducted to assess the collapse of non-reinforced masonry structure due to induced seismicity. So in order to capture the failure mechanism of masonry, which is very challenging, we developed the new material model and new features in LS-DYNA and benchmark the model behavior against different testing results. And we demonstrated that the developed material model can really capture the major failure mechanisms of the masonry structure. With that, combining with the existing advanced numerical modeling and solver capability of LS-DYNA, we construct a 3D model of each building and explicitly simulate the performance of the building and the collapse behavior. As you can see here in this LS-DYNA simulation snapshot, the progressive collapse can be explicitly captured in the analysis model, even with the collapse debris presented after the simulation. So these two examples perfectly shows how valuable LS-DYNA analysis could be in the process of evaluating of existing structures. And the strong capability of LS-DYNA with robust explicit solver and its advanced material model really make it possible to model this extreme nonlinear structural behavior all the way to failure. This could hardly be done by other types of structural analysis software. So this concludes the first part of the project showcase, where we see that LS-DYNA has been heavily used in the design and assessment process for seismic building applications. And next, I will talk about some other applications of LS-DYNA in geotechnical applications, which really start to show the advantage of LS-DYNA compared to other simulation software commonly used in this field. As for building seismic applications, which is quite standard analysis, and there are other softwares which is capable to do similar things, although not as good as LS-DYNA in some aspects. However, when it comes to the geotechnical applications, especially considering soil structure interaction, LS-DYNA really stands out, which you can see in the following examples I will talk about. So the first example is the Fremont 1A1 tower in San Francisco. And this tower shown in the picture was designed by Arup. A unique aspect of the structural system is the design is targeted at achieving higher seismic performance and seismic resiliency following Arup's developed ready rating system you can see in this picture. And to achieve this really structural innovation, such as the large mega braces with viscous dampers, as well as the uplift mega columns was considered. You can see in this picture in the rendering. And to really control, these things are conducted to really control the responses of the building and their wind and seismic event. And of course, LS-DYNA is used to model the building explicitly, and the response history analysis was conducted to help the resiliency design of the tower. This on the right shows the animation of the LS-DYNA model and a close look at the mega connections with damper and braces. While the superstructure design is heavily relied on LS-DYNA, what I want to focus more on this project is the geotechnical investigation and the effect of soil structure interaction. And there are many important issues for geotechnical investigation. While one of the most important issue is how this tower will actually affect the seismic performance of the adjacent structure. As you can see in this picture on the left, the tower, which is on the far end in this picture, is located in a small site in a congested part of the city. And the site is located immediately south of the new Salesforce Transit Center, which has a deep train box that was constructed actually simultaneously with the tower. Therefore, we performed a soil structure interaction analysis to evaluate the impact of the new tower on the transit center. As shown in the figure on the right, LS-DYNA model was really constructed to model everything explicitly in this area, which includes the below grade and above grade structures for the transit center, and the 1A1 Fremont tower and two other nearby towers on the other side of the transit center. And the 3D soil model was explicitly modeled in LS-DYNA. When subjected to bedrock propagating ground motions, the detailed 3D model allows the investigation on the demand on different structures when earthquake happens. And this shows some animation here from the analysis and some sample results from the soil structure interaction analysis. For example, this analysis provides the shear and moment forces in the trim box wall and the principal stresses in the trim box diaphragms and the shear and moment forces through cross section along the trim box diaphragm. And this results and demands from the LS-DYNA simulation really provides significant value to the design team of this adjacent structure. And as a fact, this increased demand observed in the simulation was accommodated through a relatively modest change to the local design of the train wall. So this example really shows the power of LS-DYNA that brings both the upper ground structure, the tower, and the subgrade structure, as well as the soil domain together for earthquake simulation, and investigate the effect of the interaction between the different systems, which is extremely important in this type of construction condition in dense cities. And the simulation really provides significant values to the design team. And another geotechnical application I'd like to quickly go over is the Mexico airport project, where LS-DYNA is heavily used for the design process to obtain the demand on the structure and the soil. So Arup conduct the design of the new airport terminal and the air traffic control tower, as you can see in this rendering. On the left shows the control tower, which I will focus on in this example. So both parts heavily use LS-DYNA for the design process though. So the geological condition of Mexico City is very complicated, and I will not pretend to be an expert on that, but due to the special content of Mexico City clay, as well as possible basin effect, usually the ground motion at the surface is amplified significantly, with very large side period. Therefore, when analyzing the structural response in design for doing response history analysis, considering just the superstructure with, let's say, the fake space might not be accurate. So the soil domain as well as the foundation needs to be considered in the analysis. Therefore, again, LS-DYNA has been used to conduct this kind of soil structure interaction analysis of this control tower to obtain the demands on the structure and the soil in design. But before conducting the full model analysis due to the complexity of the soil behavior there, some validation studies in the modeling procedure has been conducted. Firstly, on the left, you can see this is a very simple free field size response analysis to make sure we can capture the soil behavior and adequately amplify the ground motions LS-DYNA. And we benchmark the analysis against the historical event and record data, then to test our approach to seismic soil structure interaction, we conduct another validation study to simulate an instrumented bridge. As you can see on the right, this is another example for the validation, and really compare the simulation results against the recorded responses to validate our modeling procedure. Then the full soil structure interaction analysis was conducted as seen in this animation, which is quite impressive. And the control tower is space isolated. Obviously, the displacement are amplified in this video, but you can see how hard the isolator is working to elongate the period of the structure. And we also did some comparison on the modeling of cyclic degradation of the soil material in LS-DYNA as shown on the right here to really investigate the effect on the overall and local foundation area responses. And the analysis was not only just used to assess the demand on the soil, on the geotechnical system, but it is also used to extract the structural demands for design as shown in these sample results here. So in this project, LS-DYNA really plays an important role in design and understand how the structure will behave under the soil condition, under this kind of very complicated soil condition. And the next example I like to show is a little bit different. It's also a geotechnical problem, but it's a little bit different comparing to the previous two. So the previous two examples are kind of combining the structure and the soil for soil structure interaction analysis, which is to assess both the structural responses and the soil behavior. While this example here focuses more on the underground structure behavior and their excavation process. And in this project, we are assessing the impact of the excavation of the two towers in a very dense area in downtown San Francisco. As shown in this picture on the left, it's a very dense area. And particular interest is how the excavation process will induce the settlement of two adjacent structures. And this is conducted again by using LS-DYNA simulation. And to simulate the construction and excavation process, the entire soil domain is modeled using solid elements with layered properties, the realistic properties for each layer. And the underground structure, including the shoring walls, the excavation braces, drilled shafts, and simplified ground slab on the adjacent two structure are modeled as shown on the right in this picture. And the interface of the soil and the shoring walls are considered using a soil layer which has reduced strength and stiffness. And the interface between the pile and the soil are modeled using a special type of constraint consisting with springs to represent the realistic behavior at the interface. And from the snapshot of the LS-DYNA model on the right, you can see how detailed the underground structures are modeled in this example, as well as this realistic soil domain. So the purpose of this assessment is to evaluate the impact of excavation process, which is a very unique loading case comparing to typical analysis, say, gravity loading or seismic loading. And you can see actually on the table, this table on the left, list all the sequence of construction process of the two tower excavation. And the excavation in reality is taken, layer by layer for the soil, combining with the dewater process where the water table is lowered. And after each excavation stage, the bracing or strut would be added with preloading. So it's a very complicated process that the sequence of this really affects the response of the simulation model, which basically requires that, when you do simulation, the simulation model can really do the same kind of sequence realistically, which is removing some part of the soil domain, preload some beam elements at some point, and changing the water table at a certain time in a certain way. And this can be achieved using LS-DYNA construction stage analysis, which is a very special kind of analysis case, where you can see on the right top here, and this is a very simple examples that you can see that the soil is excavated and the brace are added. So we're kind of using this concept to do the same thing for the 3D model, to apply this construction stage analysis to mimic all these sequence listed into the real 3D model built. Then at the end of each stage, we extract detailed results to understand the impact of the excavation. So these shows some sample results after Tower 2 excavation, including the displacement contour, the load in the excavation strut and shaft. So this analysis provides significant value to help understand how this complicated excavation process would impact the existing structures. And LS-DYNA again plays an important role here with its unique feature to model complicated soil and structural interface, as well as the construction stage. So we have talked about the applications of LS-DYNA so far for seismic building analysis, geotechnical investigation such as soil structural interaction and excavation analysis. And these really are very important and common types of problems that we will see in everyday work. However, as I mentioned, for civil and structural usage, LS-DYNA has much wider usage besides this. So in the last session, I'd like to very briefly talk about some special analysis conducting using LS-DYNA, which might not be large-scale design or analysis project, but they also demonstrate the capability of LS-DYNA to tackle real engineering problem in civil and structural applications. So talking about the special analysis case, and the first special projects I'd like to show is a design of the parking garage security barrier. So as shown in this picture, you can see this is a parking garage entrance, and we like to see the option to put a security barrier at the entrance of the garage. And the challenging thing is, as you can see on the right, this is the profile view of the structural system. So the parking garage is a suspended slab, which really curved down and supported by the beams. And the location of the barrier is right on the suspended slab. We like to understand when we put the barrier here in design during the actual vehicle impact event, whether the slab can still hold the impact load, and meanwhile, whether the barrier anchorage can be designed sufficiently to absorb the impact. So two types of barrier was considered as shown in this in the bottom. And to guide the design and assess how much load the barrier can transfer to the slab during the impact process and conduct the anchorage design for the barrier, LS-DYNA analysis was used. The security barrier and the slab were modeled explicitly in LS-DYNA with mostly nonlinear shell elements, and the connection between the barrier and slab was modeled using nonlinear spring elements to simulate the behavior of this anchor bolt. And the vehicle impact analysis was conducted on the barrier to explicitly simulate the process of vehicle impact different types of barriers, as you can see in this animation. And this vehicle model was also developed by Arup's Australia office, and they have been benchmarked with impact test results. So by conducting this kind of impact simulation of different configurations, the maximum force transferred to the slab was assessed, and the stress and the deformation of the slab during the impact was also checked, as you can see here. And the anchorage design was conducted by varying the layout and strength of the anchorage in the simulation. So in this example, LS-DYNA simulation was directly used to provide important reference in the design problem and to help determine the dynamic demand on the structural system. And the next example I'd like to briefly talk about is the use of LS-DYNA to investigate very detailed local responses regarding the post-tensioning performance of the precast concrete segmental bridge viaduct. So the purpose of this investigation is to understand the cracking behavior of the precast concrete diaphragm of a viaduct bridge when the tendons are subject to post-tensioning loads during the construction. So very detailed LS-DYNA model was constructed as shown in this picture. And the concrete was modeled using 3D element, and the reinforcement was modeled explicitly using beam elements. And the advanced concrete model was used for the refined concrete to capture the cracking behavior. So you can see that the model is very detailed, and very informative results could be obtained from the simulation. For example, as shown here, the predicted crack opening width in the concrete and axial force in the rebar due to the tendon post-tensioning can be seen here. So by modeling everything in detail in LS-DYNA, it is possible to predict the general pattern and size of the cracks and their multi-axial stress states. And this really gives a very good indication of strength and ductility for the elements in question. And then a sensitivity study was also conducted on the model to investigate how the different rebar design, for example, and the loading sequence can affect the responses and the crack formation. This provides significant value to inform both the design and construction sequence planning. So in this example, we can see the very strong capability of LS-DYNA on modeling very detailed local behavior and their very complex stress states. And the next example I like to show is analysis looking into an accident of crane collapse during construction. And this accident happens and kills 7 people and 24 others were injured. So this is a real accident. And the project is really to investigate how this actually happens in the first place. And LS-DYNA was used to simulate how the crane fails and provides insights on this accident. And this slide shows the schematic of the global analysis model. A detailed model of a small section of the crane tower and the building's 9th floor concrete slabs and columns was created. And the rest of the crane tower was modeled with beam elements with crane mass modeled considering a point mass with the offset. And a steel foundation was also modeled. And the animation now shows that after the failure of the slings, it is followed by the failure of the floor tie connection and the overall failure of the tie collars as the collar sliding down the crane tower. And also a sensitivity study was conducted on the friction coefficient model below the damaged steel shown on the right here with a low value of 0.15. The crane tails a large amount with the total loss of connection with the 9th floor. So when a higher friction coefficient is assumed, the tilt is much less. You can see in this animation the comparison. And moreover, a catastrophic collapse is predicted to be avoided. So LS-DYNA modeling in this case was very useful in understanding the complex interaction between different components at varying scales. And it allows us to visualize the failure sequence and also understand some of the critical issues which affect the overall outcome. And the last example I like to show here is a fire analysis, where in this project we provide fire and structural fire engineering services for the building, which involves structural fire analysis using LS-DYNA. Usually for fire design, there is prescribed requirements in the building code. However, an advanced simulation approach was taken here first because the building height is significantly higher than code coverage. And optimization of structural fire protection is proposed, which really needs a more detailed understanding of the structural performance during fire. Meanwhile, there is an atrium connect upper floors, upper levels, which there might be a risk of fire spreading across multiple stories. So the analysis consists the typical office floor fire simulation. On the left, you can see here, and the atrium response simulation. And the LS-DYNA model uses advanced temperature-dependent material to capture the effect and the fire loading. And a series of fire loading were considered while thermal load function in LS-DYNA, as different type of fire loading might induce different effects. So through the analysis, many outputs can be obtained to understand the structural performance, such as the deflections and the plastic strains within the slab reinforcement as shown in this picture. And the analysis is time dependent. So you can see the changes of responses, such as displacements throughout the fire propagation as shown in this animation below. So this example really shows LS-DYNA's usage in fire engineering and really demonstrates the capability of LS-DYNA handling wide types of structural analysis in different disciplines. And the advanced analysis conducted really provide significant value to the fire design of this project. And with the optimized fire design, it saved cost compared to the prescribed code method. So this is the last project I'd like to show in this webinar. So in summary, we have talked through multiple real-world projects that uses LS-DYNA as an important tool to either guide the design or to help understand the performance of the system and the failure mechanism. So throughout these examples, we can see that the advanced simulation is often needed for innovative design or performance assessment for civil structure applications. And with strong relevant modern capability, as discussed in this webinar, LS-DYNA is really a good candidate to conduct the advanced simulation for this purpose. And from the example showcase, it is clear that LS-DYNA has very strong capabilities for modeling complex building geosystem behavior under different types of loading. And lots of applications are difficult to conduct with other types of commonly used analysis packages in this field. And these advanced numerical simulations conducted by LS-DYNA really proved that they could provide significant values to the engineers for their design and investigation work. So hopefully the content of this webinar provide a good introduction on the usage of LS-DYNA for civil and structural projects. We will also provide training courses on this topic later to help people who are interested to quickly get started. So at last, I'd like to thanks to my colleagues in Arup from different offices who helped me to put this webinar together and to share the contents and their experience with me. Also, thanks to the people who helped coordinate this webinar. And thanks again for your attention. And this slide shows our contact information for LS-DYNA support from different regions around the world. So if you have further questions or inquiry after this webinar or in the future, feel free to contact directly. Thanks.